Thanks, Nick. All right, so I've just quickly a little about myself. I've been here about 3 years. The Oracle Cloud Group itself is only about 4 years old. So kind of saw some momentum building here with some people I'd worked with in the past and decided this was a place I wanted to be. In my former life, I was one of the very, very early people at Amazon Web Services back in the early 2000s. Got to be a part of that. Very luckily got to be a part of that. Learned a ton of stuff. And a lot of those very same people that sort of built AWS back in 2003, 2004, that group of people is now here building this cloud, which is primarily what convinced me to come over, getting to work with those fantastic people and getting another crack at building a cloud now that we have 14 years of hindsight. So it's been a lot of fun. I've really enjoyed it. I never thought I'd be an Oracle employee, but here I am 3 years later. We've got this beautiful new office that we built, and it's been a lot of fun. So I wanted to talk to you guys a little bit today about how we're using Scala and Akka within our group to build big multi-tenant cloud services that scale out to obviously right now tens of thousands, hundreds of thousands, millions of customers. So as I was building this deck, I realized I probably had like 3 hours worth of content and I had to cut it down to 20 minutes. So I'm sorry, this is going to be a rushed talk. I'd love to talk about any of this in far more detail for as long as you guys are willing to talk after all the talks go. All right, so some things we really like in the Scala community. Cats, Akka, HTTP4S, and Play, we use both. Enumeratum is fantastic. We've recently started doing a lot more in Circe. We also use Play.json, and I really like Lee Howie's stuff as well. And then lastly, Slinky has been a new addition to our tool set. I use it personally in my personal projects. We're using it here. We do a lot of internal admin dashboards with it. But our console is built in React, and so there's a potential that we could use Slinky as the Scala.js wrapper around that for future customer-facing console development as well. So we don't use everything from all these libraries. For example, in Cats, we really like some of the monad transformers, some of the syntax helpers around ethers. That's great stuff. We're just starting to move to use Cats effects, things like that. But most of these libraries have made developing code in Scala a lot better for us. So I'm going to talk a little bit today about how and why we use Akka, and move forward here a little bit. How and why we use Akka, and sort of maybe draw an architectural diagram for you guys and how we build our systems. So primarily, why do we use Akka? There's two big things we get from Akka. One is clustering. It's fantastic. When you're building distributed systems, you either solve that problem yourself or you find a library or something else that can help you solve that problem. Akka does a fantastic job at this, and it's a tool we've come to know really well and come to trust over the years. Everything that I personally built here in the distributed system sense has Akka as its backbone. It's been fantastic. The other thing that we really like from Akka is event sourcing using Akka persistence. I think all the systems I built here as well have also all been event sourced. There's a really nice decomposition that you get when you go down the event sourcing route, and I'll talk about that more in just a moment. For those that aren't familiar with Akka, very quickly, Akka solves a number of problems for us. One of them is sort of the model around how you protect state and concurrent access to that state, and its concurrency is in Node.js. It's single-threaded access to your state at any given time. That makes reasoning about how people access and manipulate their state very, very easy to do. That's really important because when you're asking people to come in and pick up a new language, especially a language that maybe has a reputation for being difficult, a lot of the problems that we can take off the table there around how they have to think about concurrency and data access and stuff like that, it sort of removes those concerns from them and lets them focus on some of the other aspects of learning the language. And frankly, I think a lot of people are excited to come and do something with actors. You've been hearing about Erlang actors for years, and this is an opportunity to put them into practice. Message passing. Another aspect of it that I think is really valuable. I think the first two things sort of lead, and as well as the third bullet point, are what really allow you to go and build distributed systems with Akka. Message passing and location transparency are two big things. Location transparency are two really big assets that Akka brings to the table. It means that the way I write my code on my local development laptop is going to work the same way when I take it into production. Latency concerns aside, it doesn't let me cheat. It forces me to consider exactly how I'm going to communicate with the other components in my system. I think that's really valuable. We use actors in a hierarchical fashion. I think typically when you're using actors, a hierarchy, if you have a hierarchy, you're probably doing things right, if for no other reason than simply having supervision. But while actors aren't composable in the traditional sense, you do get some notion of composability once you have an actor hierarchy, and I'll talk about that more a little bit later. I mentioned supervision and fault tolerance, and then obviously the clustering distributed system primitives that get you cluster singletons, routers, groups, things like that. These are all really powerful concepts. You can go build them yourself, as we had to do back in the early 2000s at Amazon. It's a hard problem to get right, and instead we get to focus on building, building our products and our software. Event sourcing, I just wanted to say a few words in case people aren't familiar with it. Unlike a traditional application where you might create a relational schema in a database and put all your data into that, event sourcing instead just stores all the state in your system as just a series of events recorded into a journal. When you want to rematerialize the state of your system, you simply replay the journal, read the events from the journal, recreate your state. There's some really nice aspects that come out of this. There is no relational schema to manage, so we don't have things like ORMs. We don't have the object relational mismatch, impedance mismatch that, the Vietnam of software, I think it's been called so many times. And typically it's used with CQRS. One really nice thing about having the sort of journal architecture is it's an append-only architecture. And it can be very, very performant when your database is tuned properly. There's no updates, there's no deletes. It's very, very efficient. So you can scale this thing out very, very easily. Very high throughput on that single machine or at your database tier, and then very easy with CQRS to then go scale out your view side, your read side independently. This is really important when you're building massive distributed systems with lots and lots of concurrent users, because you can go tune each component of your system independently. Especially when you have asynchronous systems, right? Or sorry, asynchronous REST APIs. This is a great pattern to follow. So really, really, really enjoyed it over the last probably 5 years that I've been doing that. Okay, so what does some of our software look like here? So I'm not speaking to necessarily a specific system, but we built a lot of systems that look like what I'm going to show you here. And we're still building systems that look like this. So you have your traditional three-tier architecture. You've got sort of your API and HTTP concerns up at the top, whatever sort of protocol you're speaking. You've got your middle tier, that's your business logic, and you've got a base tier, that's where your database puts its data, right? This diagram has probably looked the same for the past 25 or 30 years. What we insert here is we turn that middle tier, we insert Akka into that middle tier, specifically Akka clustering. And that middle tier is composed of n different machines, right? This is obviously a logical diagram, and across those n machines, Akka clustering and cluster sharding specifically takes care of understanding how we take our data and spread it out amongst that cluster. And Akka does that by creating shards, a number of shards that you specify up front, and then it goes and it manages to it conspires with all the members of the cluster to go and spread those shards out evenly amongst the cluster. And once you have those shards out there, you can start spreading your data amongst those things. And as nodes come to the cluster and leave the cluster, the shards are rebalanced using an algorithm of your choosing. So you can isolate specific customers, or if you're more concerned with I/O or memory pressure, whatever it is, you can sort of tune how Akka decides to do that, or you can just go in and say, let me handle it myself. So it's a really powerful way for us to sort of ignore a lot of the complexities that come from building a system that has distributed, replicated, or sharded data like this. In the diagram here, I have these little orange boxes, with the letter T, that stands for a tenant. That's what we call our customers. It's like an organization or a group, we call it a tenancy. I want to mention that because I'll be talking about that a little bit more going forward. So typically the way we structure our applications is a user comes into our API gateway, they make a request, and the first thing we do is we authenticate the person right there at the gateway, so that every message that gets passed within our Akka cluster always carries user information with it, and that means we know who somebody is at every stage of the way. Now we don't do authorization here because we have a pretty strict separation between a protocol layer and the layer that actually enforces business logic and understands the rules of what it means to allow someone to do something. And there's a lot of aspects to that. It's not just permission-based. It's also things like, have you exceeded your limits and your quota, things like that. Have you been whitelisted for these features, stuff like that. So we don't allow that to leak into our HTTP layer, and that means our HTTP layer is very dumb about what it's doing, and we can substitute in other protocols if we need to, gRPC or whatever it may be, and we don't have to replicate any of the business logic that actually matters. So. Once that request comes in, the API gateway, again, we're very careful to hide from it that it's actually talking to an Akka cluster. We give it something that looks a little bit like a DAO. We call it a repo, just taking the event sourcing terms there. And it thinks it's just talking to this thing with some nice functions that it asks a question and it gets a response. And it's within that repo that we hide the fact that there's actually an Akka cluster there. So the request gets thrown into the Akka cluster, and the Akka cluster, based on some config that we give it, knows how to look at any given message and figure out exactly which shard to send it to. And it takes care of that for us transparently. From our perspective, we just look like we sent a message to some actor, and it just ended up at the right place. Once it lands at the shard might have many, we organize the atoms within our shards around tenants, individual tenants, and then the shard figures out how to route that request to the specific actor that represents a tenant that lives on that shard. And again, these shards can be rebalanced across nodes seamlessly, and the communication will continue to work, and Akka will take care of handling all that sort of rebalancing and management of nodes for us. So from our perspective, the application, actually a lot of this stuff, even the notion of shards, is largely hidden from us when we're writing our code. You don't have to necessarily be concerned with that. So if we double click on one of these tenants here, once a request arrives at a tenant, one of the things we like to do is, I mentioned earlier, we like to build actor hierarchies. Typically, we use this guy at the top here, this tenant, is the supervisor for all of these actors. And his job is to make sure that he restarts them if they crash. He understands how to handle specific errors for each of those guys. And he understands a lot of the concerns around collecting metrics, doing logging, things like that. So he creates all these actors and wires them up in a specific order. The individual actors are unaware of each other. So in this model here, for example, a request comes into a tenant, and he passes that message on to the auth actor, who does things, obviously authorization concerns, talking to our identity service. And that guy forwards a message on to some other actor. He doesn't know it's a limits enforcement actor, but it happens to be because it was wired up that way. And he'll go and he'll check his limits enforcement. And when if the request that's coming in is sort of been, satisfies all the limits enforcement that we need to do, he has a little function that we pass into him that says, if it's this kind of message, a query, send it to this actor, and if it's a command, send it to this actor. He doesn't actually know who those actors are, and the beauty of this, of course, is that I can insert new layers into this hierarchy at any given time. If next week we have a new concern that we need to enforce before we go and give commands to the ag or ask queries of the view, we simply insert the actor into this tree. None of the actors are any the wiser, only the tenant manager, the tenant supervisor at the top needs to know about that. You can imagine how you can use this in testing as well. I can test that auth actor in isolation because he has no knowledge about the hierarchy in which he's participating. It's very, very easy to put probes on both sides of him and test this code very thoroughly. As a result of that, we've invested a lot in our testing frameworks. We have really great tests, and typically writing test methods for these actors is on the order of 4 to 5 lines of code. So you add a new feature, there's no reason not to go write a test when that's all you have to do. So definitely encourage doing that. We have these actors down here that do views. Views and an aggregate, we call it an ag for short, is an event sourcing term. He's basically the guy who handles incoming commands. And he has workers that hang off of him as well that do sort of asynchronous background tasks, stuff like that. And again, the hierarchy really gives a lot of power in this scenario because this guy's responsible for managing those actors and dealing with failures as he sees fit. At the end of the day, back to the event sourcing bit of this, the ag, if a command comes in, update this thing, create this thing, and if it passes all of his rigor and validations, he then generates an event, and that event is stored in the database, and he responds back to the original person who inserted this request, simply saying thumbs up or thumbs down about whether or not this request was accepted. Asynchronously, we have a view side of the equation who simply is just reading off the journal. And as he reads off the journal, he updates his view of the world. It might be very different than how the ag views the world. And in fact, there could be many different views that present different projections about the state of the world back out to our query APIs or into our internal services. And in fact, this view, again, if you go back to the note I made earlier about location transparency, this view may be on a very different machine. In fact, there could be hundreds of these views that are sort of serving a very high volume of requests. Again, the nice thing is none of these actors have to be wise about that. They simply get a reference to an actor, which might actually be a collection of actors somewhere else. And so it, again, allows us to scale those things without having to touch anything else in this hierarchy. It's a really nice model. Okay. Again, I was trying to cut this short, so I'm going to, a few things that we really like to do, lessons we've learned, how we keep things running smoothly as the code base grows. ADTs all over the place. We think those are extremely important. Use ADTs everywhere. They save you. One of the complaints about actors is that they sort of break a lot of the type safety you get from a language like Scala because you have this great big receive block here that is, it's a partial function, which means you can send it anything you want, and if you don't know how to handle it, your actor will crash. ADTs save us from this. So you can see up here what I've done at the top is I have a fake actor here. I've created an ADT here called message, and there's exactly 2 objects. And down here, we just detect that. We detect that object type and hand it off to a total function rather than trying to handle it in the partial function. And now this code would not compile, and I'd be notified by the compiler because I forgot to handle the Pong message. And this is what saves you from the untyped stateness of your partial function, the receive block. We follow this practice religiously, and we can catch all the messages we don't expect, and it's always an error, or a warning in this case. We do the same thing for our error messages. There's no returning strings. We return ADTs for error messages, and again, that forces us to handle all possible errors in the cases where they need to be handled. We also, if you'll notice here, I'm not embedding HTTP status codes in any of my messages. That's the concern, again, of that very outermost layer, and my Akka layer has no idea that there's HTTP involved anywhere in this. We separate those concerns. And it's up to the HTTP layer to make sure that it handles all of these. Again, the compiler will save me if we don't handle them because it is a closed type, a sealed type, and it's saved us again. You won't get exceptions from our APIs. You'll always get well-formed error messages. Last thing that we found really is important. We used to have a trait that all of our messages would extend, and it would have at least all of these fields in it, if not more. And then all of our messages ended up having the thing they were concerned with like 12 other fields tacked on the end. And it was all this replicated stuff, and it made testing a little more annoying, and frankly, it made all the case classes very ugly with line wraps and stuff like that. And so we switched over to actually using message envelopes everywhere, and I think it's a much better practice. There's a little bit of an annoyance in that you have to unwrap those envelopes before you can actually pattern match on them, but it's a small price to pay. The other thing is that as we discover new things that we want to add to the envelope, it's only one place we have to touch. We don't have to go break all those messages. And if you're familiar with event sourcing, you also know that means versioning your schema, because now you have to be able to read the old messages that didn't have the fields and the new messages that do have the fields. So this saves us from that as well. There's a couple important things here I want to call out, and these ideas aren't original to us, but we follow them. One is, I mentioned earlier, we always carry the user around with every request, and we like embedding a deadline in these messages as well. It's great because if my queue's backing up as an actor, I can take a message off of that queue. I can instantly tell if it's safe to just discard the message completely. And I do that just by saying deadline.isExpired or whatever the function is. It's very, very quick. It's very, very easy. And I don't have to do date math all over my code. As simple as it is, people still get it wrong, and it clutters up your code. And then lastly, we embed a request ID everywhere. That's the same request ID that comes into the HTTP gateway, and that goes everywhere. And we link that up to our tracing tools so that when we need to go and sort of marry our access logs to our service logs to open tracing or Jaeger or whatever it is you like, we have a common identifier across the board, both at the Akka layer, at the HTTP layer, and everything else. And these are the things that have really helped us sort of keep the lights on, as it were. I'd love to talk about this for a long time. Monad transformers for errors, these are great. They seem scary at first, but I decided I meant to delete this slide because I could talk about this for an hour. So they're not scary, they're fantastic. Happy to talk about them later. And I think I got done in maybe under time. So we're hiring, obviously, Nick mentioned it. We have a lot of headcount here. And just to extend a little bit of what he said, we're the container native group in this office. So we own Functions here, which is like our version of Lambda, just launched at Open World. We own Managed Kubernetes, Registry. We're building out a ton of new greenfield services, which I can't talk too much about publicly right now. But it's an exciting group. We're growing really quickly. We have a lot of headcount we're looking to fill. So if you're interested, please talk to myself or Nick or any one of the other people that are here at Oracle if you want to know a little bit more about it. Any questions? Yeah.
How do you test your actors?
We use Akka Test Kit. It's fantastic. Probes are great. We have big test harnesses. We invested a lot of code in either traits or objects that live outside of the actual test code itself. We mix those in. And what that means is that the actual amount of code you have to write for any given test is very, very small. We test from the outside, right? We want to observe input and output. We don't typically try and inspect state within the actor. There's a few exceptions to that that are very specific to the services we built. But it really is sort of, I sent you this message, I expect this message to come back. I may go look in the journal to see if the right set of events were emitted, or I may try and apply that journal to our views, and then go ask the view, does the world look like I expect it to? Very much from the outside using Akka Test Kit. So. Oh, I'm sorry, yes, yeah. The question was, how do we test our actors? Yeah.
With your actor composition hierarchy you were talking about earlier, do you use types in any way to enforce a hierarchy or to provide any sort of assistance in terms of composition factors? You were mentioning the composition is done by configuration. Is there any sort of type safety you can get for your composition?
Yeah, let me see if I can say it properly. So it sounds like what you're asking is, is there any sort of type safety we can rely on when building out the actor hierarchy, the way we compose our actors? So yes, I said we do it based on configuration, and what I should have said is configuration as in code. It's all in code. That supervisor actor, it's a very, very small amount of code. The first thing he does in his constructor is he creates all the actors, passes references between them, so he wires them up in the order he wants them to live in, and then he sort of starts talking to the first one, and that chain, everyone's just doing a forward down that chain, which is why the last guy can say, send or bang, and it gets all the way back up to the HTTP layer. But we get type safety just by virtue of the fact that we're calling constructors on these actors and passing in the dependency injection, if you will. Passing stuff into their constructors, they get newed up, and we just pass refs around, actor refs around. So. Yes.
Do you find your error file getting really big since they're all sealed and need to be in the same file?
That's a great question. Do we find that our error file is getting really big? It's sealed traits, and that means all the errors in our entire application would theoretically have to be in a single file. So the answer is, define big. I think in one of the bigger services we probably have, I would guess that file's maybe 100 lines of code. There are a lot of error codes there, but it's pretty manageable. And there's not really code in there, it's just type declarations. There's very little in the way of actual functions. I think a lot of times, yeah, I wouldn't say it's huge, but that I've thought about this problem a little bit. I don't have a good solution to it. Microservices, split them out. I don't know, but. Anybody else? Yep.
Related to the first two questions, so there's typing that they introduced the Akka type. Have you looked into it, and if you look at how they compose behaviors and stuff, how do you think it will? I mean, the effort that you put in versus how it will change your test plan or testing issues.
Yeah. So I think the question was. Looking at the new sort of typed actors that have come out of Akka, how do we think that's going to change our approach to a lot of these problems? I'm not sure that I've looked closely at the latest iteration of that. I've listened to Roland Kuhn talk about it a little bit. I really like a lot of the ideas he has around it, but I haven't actually used them. I could see that definitely changing the way we approach some of these problems. There's some stuff that I think we're concerned with now that if those really do provide what I hope and expect they will, that we can get rid of a lot of this stuff that's not needed anymore. I don't think we'd rewrite our systems. I think it'd be more like new systems. We'd start exploring those things. So. All right. Thank you, everybody.